Welcome to Advanced Data Analysis 1 with me, Erik, Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 19 on assessing model assumptions, both for paired data and for two-sample data. So we'll jump down to the timetable, Class 19, and go ahead and download this R Markdown file. And the data file you should already have from a previous assignment. It is the United Nations membership data. So we'll go over to our studio, we'll open class 19, and we'll knit it. We'll also set the working directory to the source file location in case we want to do computations in the console. And then when this finishes, we will, this is something I get sometimes. I'm glad this came up. Sometimes it gets to the end of knitting. You can see we got 100%. But sometimes I get this, this error where it can't it can't read in, is that right? Well, it's having trouble writing the markdown file. So it writes a markdown file and then it converts that to HTML. And all I do is I just knit it again. And the second time it almost always works. I don't think I've ever seen it fail twice in a row. Famous last words. Let me try one more time. See? Hopefully that's just on my computer. All right, so let's open that on browser. And so there are two examples here. And the first one uses a data set on 2 sleep remedies. I think I used this example in the lecture notes. And then we're going to revisit the United Nations example as the second part. All right. So in the first one, we're going to ask about these 2 sleep remedies. So the following data give the amount of sleep gained in hours from 2 sleep remedies, right? So if I usually sleep about 7 hours and I take sleep remedy A, maybe I end up adding 1 hour to sleep a total of 8 hours. So that would be a 1 for me. And maybe B does nothing, and so I continue to sleep 7 hours, so the gain is 0. That's the situation we're in. There were 10 individuals who were in the study, and they have trouble sleeping an adequate amount, and we're hoping that one of these 2 sleep remedies helps them out. If you get a negative value, you actually lost sleep, right? So if I typically sleep 7 hours, but I take remedy B and I sleep 6.5 hours, I've lost a half hour of sleep. That's a negative 0.5. All right, so defining some notation here. The mu of A is the mean amount of sleep gained among these troubled sleepers who take remedy A. Mu B is the average gain when taking remedy B. And the difference, mu D, is the difference between these two, mu B minus mu A. And we want to know whether the difference is equal to 0, and you can also define it in terms of mu D, in terms of that difference. That would mean that these 2 sleep remedies give you equal gain of sleep. All right, so we're going to read in, we're going to load the tidyverse, we're going to source my functions, and here are the data. Instead of including a separate CSV file, it's short enough that I just included it here as text that I read in with read.table. It has a header, which is just the letters A and B. So once I create that data set here, I then mutate a new column for differences, B minus A. And here is the summary of those 3 columns. The median and mean for A is 0.4 and 0.7, B is 1.7, 2.2, and the difference, B minus A. Now it's important to remember the difference. Positive numbers for the difference indicate that B is greater than A. since A has a minus sign. And you can see, just across, say, the medians. Let's do the means, actually. That's the better way to do it. It should be that 2.29 minus 0.77 equals 1.52. All right, so now let's look at a visualization. And I'm not going to go into the code too much here, so I don't spend too much time. But I will make a couple comments. So on the horizontal axis, I've plotted A, and on vertical axis is B. And we've got the 10 dots here. Okay, I've added a vertical line at 0 and a horizontal line at 0 so that we have a sense of what's happening. And this diagonal line is where A equals B. So if points are above the line, that means B is greater than A. And if points are below the line, that means A is equal, or A is greater than B. So here, most everyone is benefiting from B more than A. There's this one person who basically doesn't benefit at all from either one because it's right near 0. And the other thing is, I want to make this a fair visualization comparison. So the scale of the x-axis and the y-axis, that sort of the distance, this might be about an inch or so on the screen, and this is about an inch. That should be about the same. And this diagonal line should be a 45-degree angle from each of these two horizontal and vertical axes. So the way I did that in the code, I've got, let's see, I do a couple things. So I'm plotting the data. I'm assigning to the x-axis remedy A, to the y-axis remedy B, and I'm going to create a few lines. So the first line is my diagonal line, where the intercept is 0 and the slope is 1. That's a diagonal line. Alpha is 0.4. That gives me a sort of a dark line, but not too dark. And then I've got a vertical and a horizontal line at the x and y intercepts of 0. Alpha of 0.2 gives me a pretty light line. So down here, that gives me this diagonal line that's about twice as dark as the horizontal or vertical lines at 0. Then I'm going to plot my points, and I also put a rug on there. The rug on the scatter plot gives me these tick marks on the x-axis and the y-axis for where each point is. For example, this dashed line at the top corresponds to this point, which also corresponds to this tick mark on the x-axis. So in a way, it gives you sort of a density marginally on each axis. Let me zoom in a little bit. Chord equal is the real key part here. That makes the axes square so that it's a fair comparison. Otherwise, you might end up with a sort of a horizontal, a long horizontal plot or a tall vertical plot, and that really skews the data. The last part is we want the ranges on both the x and y axes to be the same. And so I'm setting the limits, and up here I've run this code which takes the data set, or the values for A and the values for B, puts them all together, and it gives me the range. The range function returns two values, the minimum and the maximum. And let me see if I come down here and I run all the code. Let's set the working directory to the source file and knit this. No, that's not what I meant to do. I meant to do run all. And run all. Can I do those at the same time? Don't care about that. Don't care about that. Okay, so there's the range. So the smallest number I had was negative 1.6 and the largest was 5.5. Imagine gaining 5.5 hours of sleep. That's too much. So if we look at the data, the smallest value was negative 1.6 and the largest was 5.5. Okay, so it found those two numbers. It put those into this small list, which I call axis limits, and so that defined the lower and upper bounds. And that means that in the plot, the lower bound of negative 1.6 and 5.5. That's the same on both of the axes. That's all. It's just a bunch of little steps. These 3 lines, these lines are to make the axes the same, so we can have a good comparison. Okay, that's a lot of talking just to introduce this. The main thing, the main data that we're actually interested in, though, are actually the differences. So if we plot a histogram of the differences, x equals d, here's that plot. Okay, so these are the differences between B and A, and I've overlaid a few things here. The histogram is there, those gray bars. I've overlaid a geometric density smooth function. I'm not sure that that actually adds very much when you've got a small sample, but if we had a large sample, it sort of helps your eye smooth out the raggedness of the histogram. I've put in a vertical line at x equals 0, which is a red dashed line. And just to give a reference point, right? So if A and B were the same, then they would be centered at 0. But instead, they are centered at the mean of the difference. So I've put in a y-intercept of the mean of the D column in dat underscore sleep. I made that a blue solid line, and it's up here. Okay. I added a rug underneath those little black dashes, and I put a title on there. So now we've got a view of the data that says, all right, looks like we've got strong evidence that for each of these people, B actually improves their sleep more than A. The one comment I think I don't remember if I said or not is, clearly, each person in this experiment was subject to both conditions, right? So I'm a bad sleeper. At random, I took either A first or B first. Imagine maybe I was in a group that took B first. Saw how it affected my sleep. Maybe then I stopped taking it to get my body back to status quo, and then take sleep remedy A, and then I've got 2 values. I've got a B value and an A value, and this is my point. And for me, my difference is my B value minus my A value, basically this height, but from the diagonal line. That is my difference between B and A. So everyone has a difference, and the data are said to be paired because for each person, within each person, you've got a B and an A, and you can pair those values to take a difference. All right, and then you go through and conduct the hypothesis test. State the hypothesis, right? So is the mean the same? Is the difference in sleep the same for under treatment B versus treatment A? We're going to take alpha equals 0.05. I've got some code here that does the t-test. Now there is something different here. Let's go look at the help for t-test. So there is an option in the t-test function of paired, and that option is defined down here, a logical indicating whether you want a paired t-test. And that means that when you specify the x values and the y values, should you take those numbers, pair them together, and take the difference? Okay, so I'm specified B first and then A second, so it's going to take B minus A for each of that. The result goes into t-summary, and it says paired t-test. The data are the B vector and the A vector in that order, and when you take the pairing, it's going to take that difference in that order. The mean of those differences is 1.5. And then it's got, and once it takes those differences, it treats it as a one-sample t-test based on the differences. So the mean of those differences is 1.5. The t-test for that one sample list of differences, is 3.7, the p-value is 0.004, and you have a confidence interval for the differences, somewhere between 0.6 and 2.4. And we have specified a hypothesis test that this is not equal to 0. And we could do greater than or less than, or we could even offset it so it doesn't have to be equal to 0. And our t-statistic was 3.7. That's pretty far. You can see just a tiny bit of shading in each of these little tips, and the p-value is very, very small. All right, and so here's the places where you need to fill in things. So you filled in you've specified the hypothesis test up here, and then give the t-statistic, give the p-value, and state your conclusion. Okay, so this is all stuff that you did in the last assignment, except now you are doing it on the paired data instead. Okay, now this is where it comes to the new stuff, testing the model assumptions. So we assume that we have a random sample from the population, and this probably should say that and that the sampling distributions of our test statistic is normal. Okay, so the sampling distribution should be, or at least it should actually follow a t-distribution, but it's roughly normal. Okay, what does normal data look like? Well, it looks a bit like this curve actually. Okay, symmetric, no real outliers. Okay, so I've got in the ADA functions.r script that you sourced at the top of this code functions that help us use the bootstrap to try to approximate the sampling distribution to give us a sense of whether our assumptions are met or not. I do want you to read this description, but here is our one sample result. So this code, it's BS, stands for bootstrap one sample distribution, and we put in here the data set that we care about. The data we care about here are the differences. The top plot that it makes is a histogram of the differences, right? Centered at about 1.5. It has that one outlier out here. And on the bottom, it has a bootstrap sampling distribution of the mean. And I go into much more detail in the lecture notes and the videos for the lecture notes. But it basically resamples the data, and for each one it calculates the mean. And each of those, and it does that over and over again. And for each of the means that it calculates, it plots it down here. And so our means are centered at around 1.5, and it has the gray shape, and with that black line that follows the gray shape. Now if we take that distribution and we calculate the mean and the standard deviation, and we plot a normal distribution with that same mean and standard deviation, that gives us the red line. And if those two curves match up, the black and the red, then that says that our sampling distribution of the mean is approximately normal, and therefore we can use the t-test. Now, these curves should be really, really, really close. And the difference that we see here is probably enough that I would be uncomfortable using the t-test. We have systematic differences, and these systematic differences will tend to be very similar across examples. So our gray curve, because of this one outlier out here, this one outlier, whenever it is included, we get a larger mean than when it is excluded from our bootstrap resample. And so we end up with a black curve that is right skewed. You can see this sort of longer tail on the right-hand side and the short tail on the left. So the sampling distribution is not symmetric. And so we get the black curve is under the red on the far left, over the red in the middle left, under the red in the middle right, and over the red on the far right. And that systematic difference is enough for me to say, I'm uncomfortable with the t-test, I'm going to use a non-parametric test, which is something that we'll learn in a future class. So interpret the plots above, I've sort of said all those things already. We sort of have one outlier in the to the right in our sample, which causes right skewness in the sampling distribution, which causes deviation from the normal curve. Therefore, I would conclude that the model assumptions are not met, that the model assumptions are not met that the sampling distribution is normal. Okay, that's how I'd answer that question. In the second example, we've got the African countries example. In this case, we have two separate samples. We have people who were primed with the number 10 and people who were primed with the number 65. And recall that the people who had the 10 gave a lower number than people who were primed with the 65. And we want to know whether these two means are different from each other. And you answered this question in the last assignment. So we can calculate, we can use the t-test to answer that question. We get a p-value of 0.002, and we reject the null, concluding that, in fact, the priming effect was large enough to say that it had an effect on people's guesses of the proportion of countries in the United Nations that came from Africa. Okay, in this assignment, I just care about checking the model assumptions. So I want you to interpret these plots. And now I've got this other function. It's very similar. The only word really is that difference is we've got the bootstrap for a two sample, and we're looking at the difference of those samples. And we want the distribution of those means. So we have a first, now we've got two inputs. We've got the UN percentages for priming number 10, and we have the UN percentages for priming number 65. That creates three plots that are put all together. So on the left, or on the top, I've got the priming number 10. It says sample 1, and I've got the sample size, the mean and standard deviation. Okay, sort of a little bit right skewed. Sample 2, also right skewed. And now the bootstrap sampling distribution is of the difference in means. The way the function works is we draw a resample of size 36 from these observations. So, about a third of the observations are going to be left out, and of that resample, and other values will appear more than once in each sample. So you draw a resample from here, calculate the mean, draw a resample from here, calculate the mean, and then you calculate the difference in means. I think we do it in the order that we see it here, 10 minus 65, sample 1 minus sample 2. And that's why we have a negative value as the center on this x-axis. And we do that over and over again. Draw a new sample, calculate the mean, draw a new sample, calculate the mean, calculate the difference in means, plot it down here. Do that a bunch of times. I think the default is 10,000 times. And you get the black curve overlaid on the gray histogram. With calculate the mean and standard deviation of that black curve, and that informs the red curve, which is a normal distribution, and this one looks great. There's a tiny bit of deviation here in the middle, but the tails fall in line quite well, and these small deviations I think are not too troublesome. I think those deviations are coming from these few outliers in this sample 2. But I would say the things that I just said would make a good interpretation. In this case, I think the gray distribution follows the red normal curve quite well, and our model assumptions are met. So I would feel comfortable with the conclusions of the t-test that we did for the UN example. All right, that's everything for this video. Checking model assumptions, I will say, is a really key point of emphasis for me. The only way that you can trust the inference from a statistical test is if the model assumptions are met. And that, I think what I stated earlier, right, we need basically that a random sample from the population so that the sample represents the population, and we need the model assumptions met. In this case, the sampling distribution is normal. If those are met, then you can feel good about the conclusion that you make for a hypothesis test. If either of these are not, if either of these case assumptions or conditions are not met, then I would feel concerned. And as a statistician who observes reports from other people a lot, it is often not the case that you have a representative sample. For example, any survey that is taken from the internet where people self-select themselves into responding or not is not going to be represented, because the people who don't respond, or the people who are unable to respond or didn't even know they could respond, they are not included in your sample, and so you're getting some bias there. And then there's lots of data that just are not normal, and so you should not use a test that makes that assumption. Now, there are other tests that we'll learn about soon called non-parametric tests that do not make normality assumptions, and that's where you would change the method that you use to perform a hypothesis test. All right. Oops. All right. Hope you have a good time with this one.